טוב, למען מארגן. לא, זה...
لا זה כבר מקליט, אבל בסדר.
זה מיוט.
אני לא אכבד את ההקלטה כי אני אכבד, אני אחרי שככה להדליק אותי.
מיוט.
כן.
טוב, אתה תתחיל את המיוט אחרי זה, שלא ישמעו אותך מדבר.
אני עכשיו מתכונן לשיעור, זה בסדר.
יופי.
זה לא חלק מהשיעור למי שרואה את ההקלטה, אני רק מתכונן.
תגיד להם. יאללה, ביי, רמי, בהצלחה.
תודה רבה. אותו. But we can start with questions. Do you have any questions? No question. Everything is clear.
It's the same as before.
But what?
Only the same as before. It's for unit to you.
You didn't prepare. No, sorry, I didn't prepare. Uh, Sometimes there's another kind. So last time we started to talk about the exchange and it was a bit confusing. So let's now do base change for sets. What?
These lights.
That's how it goes. Here's the one. Questi vuoi aprire ora lì? No. Parabolic lì. Cosa ho fatto? Ho finito due. Due mi sa. Due mi sa. Okay, now it's good. So what is a representation of a set, or sometimes we can call it sheaf of a set? It is equivalent to the notion of sheaf when you consider the discrete topology of the set. So it's kind of meaningless thing. We consider the set as a category, but just know more we can set of identity, and then consider functors from this category to them. So what do it mean? Just assignment of a vector space to each point is very simple language. So sheaf on the set or representation of the set. So if we now we're working for the point of view of groupoid, so set is a special case of groupoid, so and representation of the set. And so now let's start to prove base change. So first of all, let's try to understand what is pullback and what is push forward of sheaves on set, of representations of set. So we're left or next to line. So if we have a representation of this set, so functors back, just assign it in fact of to each point, we can pull it back to here, each point in X, we see where it maps to Y, and then pull back the vector space and attach it to what is a joint functor of this functor. So there are two adjoint functors, two sides. We start this point Y, we run over all the points over its fiber, and then we can do one of the two things. We can take direct sum for these vector spaces, or take direct product of vector space. Or if it wouldn't be vector spaces but some other category, so we can take lim, the product and top. And this will be like so philo star will be product and the trick will be product. And you see it's the same for final set, so it's the map of final fibers, otherwise it's not. And now we have, like, for example, this, and we have base change diagram. So a good thing about base change diagram, and final product, yes, that the fibers of this map are exactly the same as the fibers of this map, but over different points. Or more exactly, where a point here, its fiber here will be the same like the fiber of its image. Yes? Is it clear? Everybody abstain? Who think it's clear?
What sense they are the same?
There is a nature of ejection. There is a nature of ejection.
So if it's the diagram of pullbacks, then
Pullback of sets, yes.
yeah.
Yes. It's not only commutative, it's a Cartesian square. Yes. It is commutative, but it's better than jumping. Yeah, what is the fiber here? It's just all the pairs of point here that maps to the same point like the imaging. So it's exactly the fiber. And so
If with x2 is a fiber product of y2 and x1 over y1.
what? X2, yes. Two. Yeah. So I said last time that although fiber product, the Cartesian square is completely symmetric construction, when we think on it in terms of wave change, we don't think about the words of these guys are symmetric. We think of x1 as a family of sets parameterized by y1. Each point in y1 gives its fiber, which is said. And we think on like no the next one, this L, this part of the diagram. And this part of the diagram is a reparameterization of the same set, of the same family. So we take now a new parameter set, y2. So if the map is onto, you really can think about it as a reparameterization, but if it's not onto, it's a reparameterization of some part. And we just take the same fibers, but now we name them with different names. The names point and y. This is a good way to think about fiber product, especially like when you say base change, it means that you see places. Okay. So now what is it? So base change is both this diagram and you can say that this arrow is a base change of this arrow along this map. This family is a base change, base like a parameter set of this family. But also it's a statement. So what is a statement of base change? That if we take a representation pi and we take first of all we can push it down. And then we can pull it back. The name. Then the same as first of all pull it back. And then push it down. So why? So it's trivial to prove, but before we prove it, I just want to say what's the meaning. Yeah? So we have here a family of sets, and we have on the global object on x1 we have a representation or shift. But since x1 we think about it as a family of sets, we prefer to think about this global object as family of global objects on each of the fibers. Yeah, so we have many fibers on each of family. So instead of thinking on pi as one big sheet, one big representation of x1, we prefer to think about this as family of representations of each for each point in y, representation of its fiber. And indeed, if we have y1, y2, sorry, x1, and here we have just one point. So here we will have the fiber. So having a sheaf here you can pull it back and get a sheaf on each fiber. Or having a representation, you can pull it back, get a representation on each one. But of course, the other ways around is not. So in test sets, the other way around also too. Once you have a sheaf on each fiber, you can just sheaf is just corresponding for each point vector space. So you know for each fiber, for each point what's the vector space. So you also know for each point, but any point in some fiber or any unique fiber. But in general, when you will have some other structure, some other category, some topology, or whatever, the other way around will not be true. Because things have to kind of glue together to make some sense. For example, if we will talk about actual shifts over topological spaces, so shift give you in each point a vector space, because you can pull back shifts point. It is correct, but you cannot. But you can just by knowing what happened in each point say what is the total shift, because the shift actually give you some global structure, some interaction between the points, whatever. But still, at this data of shift of each fiber is you can think of it as one big shift here. So basically saying that it comes from one big shift here means that this is not just a random collection of shift with each fibers, but some reasonable family. So now we have the construction of phi 1 lower star. So on each fiber, we just take the direct sum or the product. The product of all the fibers. Some global operation, in our case, just taking a fiber product. And now we want that. So what base change says for this diagram? It says that for each fiber, for that you can first take this global operation and then ask what is the fiber as a point, or restrict the fiber and then take the global operation. And this means that this global operation of push forward actually reflects taking for each fiber global sections. And this is why we like the base change. So now let's prove it. Proof.
And in this equality, P2 must be.
I don't know. What?
Oh,
P2, yeah, lost. It's isomorphism, so to be more accurate, we need to say that if pi range over all functors to vector or representations, we have here isomorphism of two functors. But of course, we will just prove it on the level of objects because we expect to be that the isomorphism will be kind of tautological. Yeah. What is this? So let's plug in the point here. Yeah. Or let's start with it. Never mind. Alpha star, phi 1. Both star, half pi. So this is a shift on y2, so let's plug in the point y2. Oh, y is pointing. So what is going to be? Can you help to write the formula? So as usual, we start from here. So we pull back some shift on y1. And we ask what is value in point 1. Y. So we have to send y to y1 and then ask what is the value of this shift on this point. So can you help me with the value of this shift on this point? Shift of functor.
Could you explain again how this P1 over stuff?
It's not really Android. Right. So P low star of pi at point x is the product y of the sort of point y x y inside inside the pi. And if you do lower shrinks, then it's a product here. Okay, so now you so how we do it? inductive product over all x in the fiber of this guy. P1 inverse of sigma. This is the left hand side. Equal. I'm going to take them off. What is the right hand side? Let's get that here with the right hand side.
We can try to write it on this. The right hand side, find it over y on the right hand side, must be. It's a problem. Or fibers of x goes by 2 units, so that right there, and in multiplying the layers of pullback of P under pattern. It points out.
So how we do it? We can plug in the beta of x and then plug in
Yeah.
Okay, so we range all over the fiber of y2. And for each object in the fiber, we'll take the image here, take the vector space by gives us, and then take up on. And now this is obviously the same, because the fiber, by definition, the fiber of y2, so of y under phi2 is bijective to the fiber of alpha of y under phi1. And the bijection is exactly given by pi. Sorry, not by pi, by beta. And so we take two bijective things, use the bijection. Once we take the vector spaces on the right hand side, and so here we take the vector spaces on like on the fiber next one. And here we take the vector space in the fiber next two. And the vector spaces are defined to be just the same vector spaces under the bijection. So the two products are going to be like this. So this is big change for the representations of sets. Okay, it looks stupid because we don't have any interesting structure. But now, very similarly, all of these carry out for Google.
Also for free, you have the same statement for
What was?
lower tree.
Yes. Lower tree instead of that product with that. Usually it's not like in the 6 phantom formalism quadratic. So if you have some geometric objects, like in our case sets, and then some algebraic objects that related to them, in our case a category of representations of set. And then you often have many functors, pull, push, etc. And so often you have two kinds of functors. You have pull and push with star and pull and push with shrink. So they call it direct and inverse image. The star ones, and the ones with the shrink sometimes called the proper direct image. And they always have to be adjoined, so the star have to be adjoined to the star and the shrink to the shrink. But for the other sides, they don't remember the sides. Now in our case, the upper star and the upper shrink are the same. So basically one functor we call upper star, and then this functor has two adjoined. One of them is lower star and the other is lower shrink. But in general, we'll have four functors and not three. And then when you want to do base change diagram, you have to be careful. So if on the horizontals you put star, on the verticals you have to put shrink. And the other way around. In our case, the horizontal we can put star and vertical shrink, which is the shrink case. But we also can say that on horizontal we put shrink, which is the same as a star, and then we put it on the vertical. Yeah, so for example, for topological space, the reason why here we didn't see any difference because everything is discrete. But in general, for star and shriek to be the same, you need some local properties. So basically, that you have a map of topological space that is locally an open embedding. So if everything is discrete, so everything is locally an open embedding because embedding of a point to a set is an embedding. But in topological settings, it will not work. But yeah, for now, it will seem to work very well. So now I want to discuss groupoids. So we define a limit of groupoid for diagram of groupoids, and this was very simple, unlike inverse limit, which we only axiomatically defined and still didn't just construct, and I still owe you this next time maybe. But the limit is very simple-minded object. One, two. So what are the objects of X2? Objects of X2 are just the following data. Element X1 into 1, object 2, and multiple mu from epsilon. This one.
Those are groupoids.
What?
Those are groupoids.
Yes, now this is diagram of group. This is a Cartesian square of groupoid, and I just recall what is.
But you know, why you think that of the objects in X2, you have objects in X2?
Because you stay. X1 here and Y in Y2 and here on the power. Maybe we put X. So this is a Cartesian square. And now, if you have another Cartesian square, if this is a Cartesian square, then the total thing is also a Cartesian square. So we're not going to kind of obvious. And this in particular means, so now we can consider fiber of a map functor between groupoids. So a fiber of functor between groupoids is just a Cartesian fiber product. Yes, we have X and Y, and we have a point Y and Y, point Y. We can consider its fiber. Let's define the fiber. And if this is the way we define it. So now what does it mean technically? It means that you take all the object in X together with a morphism between the image of this object to Y to your point. When you take this definition and plug it in here, this is what you want. So in particular, we say all the points in X, but of course, I only allow to have points which are which lies over Y in the sense that the image is isomorphic to Y. Yeah, it's groupoid, so morphism means isomorphic. So this is a fiber. And if we have a Cartesian square, then the fiber of point of an object here, the same like the fiber of its image here. This is exactly because we can take this Cartesian square and put it here. So we see that the fiber of point in Y2 is the same like fiber of the one point in Y1. Okay, so now we want to define the push forward, and push forward is exactly the Khan extension. And we know how to define. So if we have a representation pi here, now this is not trivial object, it's not just a qubit vector space for each object, it's also a morphism for any two space if we have automorphism. And for example, if x1 is Pg, then this simply is exactly a representation of G. So it's kind of meaningful object. So now we take so what is the lower star of pi? Before we had the direct product over the fiber, but now the fiber is a category. So we don't just want to take the direct product, we want to take limit over this two. So this is equal to the limit of pi, say restricted. I write restricted, but I will explain what I mean. Pi inverse of. So what it means restricted, so phi inverse of x is it's not really a subcategory of y, so maybe I will write it more carefully. So we have I x, let's call it from phi, not x, it's y.
What do you find?
So I y is made from phi inverse of y to x. So we have functor, a forgetful functor, say from here to here. We have object here, its object in x together with isomorphism from its image to y. Image and of. So we have this IY. And now instead of write restriction, I will write I of. So it means that we forget about the morphism and just look at the object in X, and then we have a vector space that we can assign to it. So we get functor from the fiber to vector spaces. And then we take limit over the fiber. Limit over. What is the fiber by
Premise. What do you do? Are you defining phi lower star?
Are you recalling the formula for the Khan extension? Yes, for phi lower star in this case of 2 points.
This the kind of extension of pi into vector, like you have
Another phi on the pi. I have
a long pi of phi, no?
no.
Opposite? Okay.
We have pi, we want to extend it to a function defined from y. Or let's do it here. We have pi here. Pi here. Okay. We want to kind of extend it, it's not really an extension, to a function defined from y. This is my phi, so we extend this functor to a function. Not really extend, but construct the functor here based on this function. So call the Khan extension of phi along phi. Or just phi lower star of phi. Or the push forward of phi with respect to phi, or the direct image of phi with respect to phi. Lots of synonyms. And the idea is that for each object in y, we take its fiber, but the categorical fiber. In general, categories is not really, it's what's called a wave fiber, I think. So we take an object and just a morphism, not necessarily isomorphism, from its image to our form. But in our case, everything is 2 points, so this actually you can think about the fiber. So not all the object that maps to something equal to y, because you forbid to say equal, but all the morphic objects that maps to something which is isomorphic to y, but you're also forbidden to say this. You should say pairs of objects together with isomorphism from its image to y. So this is fiber. This fiber, I think of it as a subcategory of X, in the sense that I have a forgetful functor to X. It's not fully faithful, but faithful. So just forgetting the morphism, just recalling the object. And now I can take my functor pi, that was defined on X, and restrict it to this category. So basically just consider it on the values on the object themselves, and take limit over the category pi inverse. And this is exactly the formula for the right Khan extension thing, and the left Khan extension will be co-limit do exactly the same thing. Yeah, in general, in can extension, you have to be a little bit careful because the definition of fiber changes the direction when you like. If you do left can extension, you have to take one direction of morphisms, and the right can extension another direction of morphisms. As we're talking about the point, so we don't. The left and right can.
What's the difference between your like left hand extension? What's the difference between the fibers of left hand extension?
Because you don't really take the actual fiber, right? You take pairs of objects in X.
Yeah.
And morphism U from
Isomorphism.
phi of X to Y. No. Now we're talking about groupoid, so you can say isomorphism, and then the direction from. But in general kind extension, you take a general.
Why?
And then you have to remember what side is what and take what more.
And what's the left right? Like why does it matter left right? Yeah. Well, does
Now you take the limit of the fiber of the restriction. In left you take limit, and in right you take point.
yes, but the fiber.
But also the fiber in left it's like one direction, I don't remember what, and in right extension is the other direction.
Morphism from Y to 5. Oh,
But we're working now with groupoid, so we don't need to think about it. So you always can think about this direction, take second position. So anyhow, you have so the formula for the push forward is a limit over the fiber. And now I want to prove the base change. And I tell you that now it should be trivial. Because I take push forward and then pull back. And then ask what's the value going to be on specific point Y. So let's do it. Alpha upper star, phi upper star, phi, 8 point Y. Almost the same as here, but instead of taking this Y is in the wrong place. It's in Y2. We have to first get it here. So limit by inverse of alpha of Y. Alpha is valid. I alpha Y. And now let's do the other guy. Now we must have this one. Not fair. I will do it here and then no. So we do. So what is the other guy? I have first of all I take the limit of the fiber of this point, but of what? Of the pullback. So let's do it. Y beta upper star of phi, and then we plug it into phi to lower star. 8 point Y equal to limit over 5. Here equals 5, here we need to write by 1. Here 5 2 inverse of Y. Of what? Of phi pi, not pi, I get pi of let's see. So okay, we should do the pullback I Y upper star of another pullback beta star That's fine. Oh. Okay, now again we see that this diagram and this diagram are the same, have the same shape, in just the same category. Oh, canonical equivalent categories, but depending on the definition of Cartesian square or fiber product that we choose, we can just assume that they are the same. And here we have pi that will restrict. Okay, we have equivalence of two categories, one diagram and one category, and then we put it back to another category. So we get the same diagram. So the limit going to be the same if we have equivalence of categories. So limits does not change. They are non-linear. So this should complete the proof of base change. Do you like it? Reasonably? Oh, now I want to do an example. You can consider it as an application of groupoids and the notion of base change, but of course it is like overkill here. You can prove an example much easier there. And in fact, the example is equivalent to the base change, so you can just consider this as a proof of base change. So what is our example? We have BG, and we have two groups that maps to G. I will think about them as subgroups, but it doesn't really matter. BH1 and BH2. And now we have the base change. So do you remember what is this base change?
It's the free.
No. Free is when you do push-outs. Here we do fiber product, much easier.
Oh, so it's a product and you identify
This is one of the union of stabilizers of the system.
That makes sense. Absolutely right. So the funny thing is, although this was like connected groupoids, have only one isomorphism class, or only one object class, and this have an object, and this have an object, the product have more than one isomorphism class. Because what is object in a product? It's pair object here and object here that maps to the same object here. But there's nothing like this, so we have to take object here, and an isomorphism between them. So although there is only one object here and only one object here, there are plenty of isomorphism between them. So a priori, our set is kind of G, yes? Now, not every two isomorphisms here are not isomorphic. Some of them are isomorphic, but some of them are not. So, in fact, when you consider it as a quotient groupoid, it's in this quotient groupoid. You have a natural relation of H1 times H2 on G. Yeah. And
These are the objects.
so the object is going to be G, and H1 times H2 going to be morphisms. So I mean that for each object, morphism forms this object somewhere are elements of H1 times H2. So H1 then mapping to somewhere, and then H2 to somewhere else. So you take it, you multiply it from the left and the right. So for some concrete other object, the morphism will be the collection of pairs of elements that actually maps our map G1, object G1 to an object G2. So the isomorphism class is going to be the double coset, and the automorphism is going to be the stabilizer of the double coset of a point in the double coset with respect to the two-sided action. So this is equivalent to a coproduct of when say I run over all double cosets. But I want to represent this like this. And here we take G H1 G inverse. You can do it the other way around, doesn't take it. This is exactly the same. So and of course we take B of this. So this is the automorphism group of the one. So this kind of a bit surprising construction. We started with points which are actually groups, so we think we're working in group theory, and we are going working in group theory, but the answer that we get is not a group. If we want to phrase it in group theory, then okay, we need to say we have many groups. So now let's do base change. And this is what's called McKee theory. So who taking in parallel Gaussian representation theory? So you probably see it there. You take representation pi. So what is this upper star with respect to, let's call it phi1 and phi2 and alpha beta. So what is that? Now we consider H1 and H2 as a subgroup of G. Can work otherwise, but let's do it with help. So what is phi alpha star, phi1 alpha star of a representation? Yeah, I start with representation here. So no, so I want phi alpha star. So what is, but still, let's start. What does the notion of phi alpha star means?
Induction.
So this is already the answer to the more complicated question. And phi lower star is induction, and phi upper star is just restriction. So phi1 upper and lower star pi is just induction of H1 to G of. So what McKee theory asks, what happens when we take induction from one subgroup, and then we want to restrict it to another subgroup? H. So restriction is just alpha lower star, alpha upper star. So McKee theory asks what happens when we start here, push here, and pull back. And the answer should be in these terms. So what is beta upper star of pi? It's kind of confusing, but you can't really write it as a representation because it's not a representation, it's a representation of 2 points. It's a tuple, yes? It's a representation for each isomorphism class. Okay, so let's understand what's happening in each isomorphism class for each G. So for each G, just pull back from B of this thing to B of this thing. So just restriction. We take pi and restrict it to G H1 G inverse. Like with H2. I don't like this way of writing. Because here it's a representation of H1, so it doesn't really make sense to restrict to something which is not subgroup of H1. So I will change the role. So we can change here the roles without changing anything. Potential. So let's change roles. Because these two things are isomorphic. So H when you wait. So you have this tuple. But this is not a complete answer. Still to write for something. But the pullback is going to be this tuple for each point, this representation. And now we have to push it forward. So what does it mean? We have to take direct product over all points. And for each point to take the push forward. So instead of writing tuple, now we can just write product over G in G H1 H2 up to all of the. And each of these guys we need to push down. What does it mean push down? Induction. H2 is also a subgroup, pushing down to okay, pushing down from this is a subgroup of H2. Now, okay, now we have to pay the price. at some point we'll have to play the price. So we take induction. So we take induction from this group H1 G H2. Maybe I should have paid the price before. Two, sorry, two, but we can't really take from A to H2. We should write like this, but then we just reinterpret it as a representation of H2 because it comes to H2. So at some point we'll have to take it back. And you probably saw this formula in the post in representation theory. If you didn't saw it yet, you would see it in another post, another time. And this is rather easy formula you can prove just with the definition of induction, because what is induction? Induction is a collection of functions from G to pi, which have nice behavior with respect, say, from the left action of H1, and then the action of G is from the right. Now, when you restrict it to H2, instead of acting with G from the right, you're acting with G from, you are acting on H2 from the right. And then your representation naturally splits to the direct product of representation for each orbit of H2, for each like double coset, because you have nice action, you have nice behavior with respect to the action of H1 and the behavior, and now the action that you care about is the action of H2, so each coset is going to be H2 invariant subspace. Or subspace or quotient space, if you want to do that. And then you just analyze what happened in each orbit, and you see that what actually happened is another reduction. Actually smaller reduction. And so this is very convenient. In theorem, it allows you, the right is very convenient in representation theory because often you want to compute I wrote this induction, but if I write product, I have to write, of course, capital induction. So capital induction is the one which is facing right adjoint restriction, and little induction is a left adjoint. For fine groups, you have both right and left adjoint. One is going to be all functions that can be bigger, they are product, and another all functions which have final support modulo H. Okay, that is good. So like capital for 2. So often in representation theory, you want to know what are the morphisms between these two guys. So you use adjunction, you use the fact induction is adjoint to a restriction. So I think the right adjoint. So we'll put here, we can move the restriction here. And then we want to compute this. And this will do it. And so there is an unnatural way to usually make it theory formulate being because you choose a representative, but you can do it without a representative. Just a way to say just the state is base change for both points. But of course, when you want to encode it, so we want to do it with representative and get. This is not the encode it, decode it, sorry. You want to go and then you get back to that. Okay, let's take 15 minutes break. Should we do photo? That concludes the development. פעם משתף פעולה? שהוא שביעי מעלות? רק שזה היה פעם.
במאי לא פתאום. הסיבה סטודנטים, אני לא מבין.
הוא לא הבין מי זאת?
אה?
הוא לא הבין מי זאת? חשבתי שהוא הבין. تمام كده؟
With that, which is. Yeah.
אז זה גבול, על פי הקטגוריה הזאת, של הפונקציה הזאת. הקטגוריה הזאת היא דיאגרמה,
כן.
מה הקודקודים שלי גם על אובייקטים ב-Y, יש עוד מידע, אובייקטים סליחה ב-X1, יש שם עוד מידע, אבל מעל כל אובייקט אנחנו דוחפים מרחב וקטורי שפאי נותן לנו, אנחנו מתעלמים מהמורפיזם.
סוף סבבה.
אבל יש מורפיזם בין האובייקטים, זאת אומרת זה לא סתם מכפלה ישרה של כל הדברים האלה, זה גבול. בפועל הקטגוריה הזאת אומרת להיות מכפלה, קו-פרודקט של ביג'ים, וכל אחד מנותן כל הדברים.
Those are votes to put it in.
Right, can you try to answer one question? Suppose we have some figures. Diagram.
What is the opposite?
This is a function from G to C. This is some null. This is the diagonal. And suppose here we have some left adjoint, here we have just move forward with this left adjoint. Now this diagram obviously commutes.
Yeah.
We have a statement that
It's not a base unit yet.
but this is a very similar statement that you have some commuting square and you obtain some different commuting square for adjoint functions.
Yeah.
So
You
here
want
we also
to have that commute. So if L is not a joint function, that's a general function.
you
Then
don't
still have everything, and you do have something. You do have a morph
Yeah.
between. But you ask why is this function commute with colimits?
I'm asking why this statement looks exactly similar as this statement.
So I don't know how to answer it, but we can break this into two. Any functor, even if it's not commute with limits, it's vaguely commute with limits. Vaguely. Wait. You have a map. You have a morph from one this follows. This is called for any commutative diagram. If it is Cartesian square, then it also really commute. So you ask whether this is a Cartesian square, maybe it will be Cartesian square if L is left adjoint. How would I want to know? Maybe.
But could both these statements be just like but specific cases for some more general statement about joint functors?
So maybe okay. Here I did everything with a point. So you can do it for general categories, but then you probably have to be much more careful. So assuming you have it for general categories, maybe this is a statement that you're looking for at this base change for general categories. And here maybe it's too difficult in square with this joint function. Whatever. So we can continue. Let's do Van Kampen theorem. So do you know what is the fundamental group? So Van Kampen theorem is a way to compute fundamental group of push out of topological spaces. So usually you want two topological spaces and some open intersection between them. So push out along an open set. So you have one topological space that have two open sets, and you have the intersection, and you want to compute the pi one of the union in terms of pi one each of them and the intersection. And if everything is connected, then you maybe know the formula. Pi one there is x1, x2, and the total thing is x. This is pi one of x1. We take amalgamation product over pi one with y with pi one 2. Here we have x, and this is pi. You know the theorem. So if you remember that it's proof, it's a bit. Sorry. It's a bit complicated, and one of the reasons is that, like, part of the argument is two-dimensional. Yeah, so the fact that you have a map is obvious, more or less, and the fact that this map is onto is also rather easy. Sorry, no. Maybe even the fact that it's onto, and certainly the fact that it's onto one. You need to discuss. I think with the one-to-one part, you need to discuss homotopy with passes, which is kind of by definition something that has to do with square, and then you maybe remember you can break the square into small pieces and do some induction on the pieces and move on the pieces gradually, and then and this is not nice, no, not very nice. And somehow a bit more basic fact is homotopy lifting theory for covering, so that with passes, and then there everything is one dimension. So if you have covering x equal to x, and you have a loop here, then you can uniquely lift it. So if you know where to lift the first starting point, you have a unique way to lift it upstairs. And the proof here is in a sense similar to this, but much simpler because it's one-dimensional. You instead of breaking two-dimensional lift pieces, you can take interval and break pieces. And you can expect that everything should work. The one-dimensional arguments should be enough, because at the end, like, what is the homotopy of passes? It's pass inside the space of passes. So you can, or you might want to work like each time with one-dimensional thing and ignore everything else. And this language does not allow you to do it easily, but the language of points do allow you to do it. So now I'll give a proof which is in this sense simpler. Of course, overall it's more complicated because it uses a lot of theory, but it somehow moves the difficulties, geometric analytic difficulties, it moves it into algebra. Okay, so let me try to give a proof. So first of all, we have a nice figures egoist. First of all, we have the notion of fundamental groupoid. So do you know the notion of fundamental groupoid? Was not discussed in the game? So yeah, fine. Yes, it was. So for any space X with pi1 of X, point, objects are point of X, morphisms are passes after homotopy, and composition is concatenation process. So this groupoid, if your space is connected, have no more information than just the metal group, but in a sense it's more canonical because you don't big approach. And if it's not connected, it's kind of have the information of all the fundamental groups of all collected components. And now we have representations of this, or not representation, just functors to sets. So pi1 sets, the same like functors from pi1 of X to sets. And so we have this category. And so let's consider this category like this. And this category is equivalent to the category of local systems on. Did you see this
The
equivalent?
degree of functors.
The pi1 sets is by definition functors from pi1. Oh, G set is G is a groupoid, gamma set, gamma is a groupoid, is a functor from gamma to set. And you see that if gamma is PG, then it's exactly G sets. It's similar to what we said before in representations, but now to sets and not to vector spaces. So, what we have here. So, did you see this equivalence? In this course? In TA sessions? Or in local systems are covered. Category of covered. Right? So the over subcategory is over category where all the maps are local isomorphism. No, they are locally on the target look like projection from a point. Okay, let's do this equivalence at least for one direction for each pi1 set. We want to. Oh, that direction is the other one. So if we have a covering, so let's put f of 1 to x. We want to give it a functor for pi1 to sets. So now we have a point with the fundamental groupoid, which is just point in x, equal to by inverse. There's a fiber of this one. Now, how is it a functor? What happens when we have a morphism between two points in x? And it means that we have a pass between 2 points in x. Then we can use the homotopy lifting theorem and lift this pass for each point in the fiber to have pass between the point in the fiber and the point in the other. Which is called a synthetic transformation. So we have map between one fiber to another. And it doesn't really depend on the pass, only on the small. So this is not completely trivial theory, but all the proofs there are kind of one-dimensional. You don't really need, you need some assumptions. You need that x will be locally simple. Because otherwise, you don't have them autonomy. Yeah, so now we can ask why it's fully faithful and essentially subjective. For fully faithful probably is very easy. And for essentially subjective, you need the construction of universal coupling. Universal coupling. And once you have the universal coupling, you can, so you have construction, you have x tilde, x. Now you have some G set, pi1 set. So yeah, this will be easier to do with the classical language. Say that x is connected, you can do it for any connected component separately, and you have pi1 set in the like pi1 set, pi1 set. Then you have this construction with tilde times z, and you quotient by the Boolean relation given by the action of pi1. Yeah, so pi1 acts on x tilde by that transformation, and pi1 acts on x because z because pi1 z, and then you have this Boolean relation that you say acting here and acting here should be the same. And this also the covering effect, and this is the covering that corresponds. This give you the other way around. So G, let's call it G. G of the so somehow the hardest thing is to construct this functor for the 3 by 1 set. Once you do for the 3 by 1 set, you just get the inverse of that. And probably there is a very simple way to say it for the dimensional points, but I don't prefer to say that. So, so we have this equivalence of contiguous. And now we have a push out the other of the topological space. Push out the other of the topological spaces. We have x1, x2, y, and what we want to prove? We want to prove that the fundamental groupoid of X is exactly the push out of this diagram. So basically, the procedure of taking fundamental groupoid commute with the push outs. By 1 of x2, by 1, 5, by 1, 1. The way functor that this is very easy because fundamental groupoid functor. Okay. It's a two functor, but in this case, very explicit, yes. Fundamental groupoid if you have a map between topological spaces, so you map points to points and passes to passes. Homotopy passes will be mapped to homotopy passes. So you want to show that this is a push out diagram. Now, what does actually means about the fundamental group? It's not obvious to state. So in case where the Y is connected and all the 3 guys are connected, then this is in fact BG for the fundamental group, this is BG for another fundamental group, this is another BG, and we did discuss push out of groupoids of type BG, which is just push outs of groups, which is just the motivation form. So in cases like the simple cases of uncommon theorem, we know what is that. So what happens in a general case? So one way to phrase the answer is this one. This is a push out diagram. Now we can ask what does it actually mean on the level of fundamental groups. So X not necessarily connected, so it has many fundamental groups. And these guys have many fundamental groups, and somehow they all have to be connected together. And maybe we'll do one example. So I did not discuss the general. I didn't give a general construction of push outs of groupoids, but let's do one very simple example. We have 2 points, or maybe I'll do it like this. We have 2 intervals with intersection, which are 2 shorter intervals, and we construct a circle as a push out of 2 intervals along this intersection. Yes, so what is our groupoid? So points are very stupid. Here is 1 point, here is 1 point, and here is 2 points. So the fundamental groupoids have no morphisms, and only eigenmorphism classes. Here only 1 eigenmorphism class. Here 2 and here 2. And the map is like this. And what is the fundamental groupoid here? So my topological space is a circle, and I present it as a push out of 2 intervals. X1 and X2 are intervals. Y is the union of two intervals, and x is a circle. So pi1 of x1 and pi1 of x2 is just the trivial groupoid. Pi1 of the intersection is this cubic groupoid, which is a set, just two elements, two objects, and no more
Pi
things.
or small pi?
What?
Capital pi or
This is the diagram of capital pi's. Small pi is going to be trivial group, and here I don't know what they're going to be because there is no small pi for non-connected space, so at least I don't need to do.
yeah, but objects of one must be points. You have the local space, so.
I replacing the diagram with equivalent stuff. Yes, you're right. So here you have like huge amount of objects, but they're all isomorphic and there are no automorphism. So this groupoid is equivalent to a trivial groupoid, and this groupoid is equivalent to trivial groupoid. This one is not equivalent to trivial groupoid because there are two connected components. So two isomorphism classes, but each of them is equivalent to the trivial groupoid. So we have here a diagram of groupoids which are actually sets, but we think about them as groupoids. What is the push out of this diagram? It's a complicated question, but you know the answer just by looking at the topological space.
Apart from point A to point B, one point. One isomorphism plus point.
So in fact, you only have one isomorphism class. Because apostol you know that S1 is connected, so the fundamental groupoid of S1 is just one isomorphism class. But you have a morph. So what you actually have here is B of C. Now you know that this is true if this theorem is true, yeah? It has to be true. And now let's see how we can see it, although we didn't do the general computation, but let's see in this case why it kind of makes sense.
Arrows must be built.
What?
Arrows must be built to there.
Else will be in the opposite direction. So what's going to be our fundamental groupoid? So the idea is that we glue. What's going to be push out? The idea is that we glue this thing with this thing along this thing. So on the level of objects, we have two objects. This object and this object. But those two objects are going to be isomorphic, but we don't, when we just do the general construction, we don't glue them. Yes? Now we ask what are the morphisms between them. And the idea is that there are two ways kind of go from this one, from one point to another point. We can go, they're both isomorphic because they're both coming from this point and they're both coming from this point. So we have two morphisms between these points. But we're talking groupoids, so we also have the inverse morph. So the two points are isomorphic, so on the level of isomorphism classes, we can choose one of them. And then we basically take the free thing here. So usually we need to factor by something because there are some equivalence relation coming from relation here, but now everything is trivial, so there are no relations. But still we can go like this and then backwards. And we can do it many, many times. And basically this is what we can do, and we can go to the other direction. So the automorphism of each of the points going to be Z. Yes, so once we will know the explicit construction of push outs of groupoids, we will be able to deduce that pi1 of a circle is 0. But it's much easier just to prove that pi1 of a circle is 0. But yet, so the Van Kampen theorem have meaning also in the case when the intersection is not connected, which the classical Van Kampen theorem usually they don't formulate it. Of course, sometimes they do formulate more general statements, but then they're kind of complicated. But the most general statement that you can formulate very shortly, that this is a push out the other. In a short formulation, when you try to unwind what does it mean, you get some complicated formulations of the Van Kampen theorem for general settings. So let's start it out. And the idea is that we're doing here some kind of unedel level. So for example, we have two groupoids, gamma 1 and gamma 2, and we have a functor between them. And now we have phi upper star between one, gamma two sets. Oh, no, maybe gamma sets to gamma one. So suppose that phi pastel is equivalent to categories, then I claim that so is phi. This should follow correct with the lemma X. So here, let me go. Okay. How do we put it? Should have prepared it better, sorry. No, what is that? One is equivalent to it should follow from the another lemma. So we have gamma 2 next to gamma 2 sets. Okay, it should be easy. We don't need because we can use maybe there are more elegant code, but we can use the classification of copoids, and the copoid is components of PGs. And then we have a functor which maps some isomorphism classes to isomorphism classes, and it depends when it will be BG to BG.
Yeah, say that gamma one opposite is just a full subcategory of gamma one sets. Same thing for gamma two. And equal back here is gamma two opposite to gamma one opposite.
Yeah, but
So
I'm not sure it's true in general. It's true if he is the equivalence of categories, but I'm not sure it's true in general.
I think it's by definition. But
You think it's true in general that it carries representable functors to representable functors? Why? You have a representable functor in gamma 2, why would you get representable functor? I think in general it's not true. But that doesn't really matter. So, okay, let's start with the case of BG. If you have BG1 and BG2, and you have a match between them, which gives you equivalence of categories of G1 set with G2 sets, then of course they must be isomorphic, yes, because you just take the free set, the free G2 set. Oh, yeah, what we want to put, why it's 1 to 1, so let's see what we have. G1 and G2. So if this map have a kernel, what does it mean? It means that we will not get all the representations of G1 when we pull back. We will get only the representations which are trivial on the kernel, which are not all the representations, because always you can construct not representation G set. Like the regular G set is not trivial on the kernel, so we don't get it. So the map has to be 1 to 1. Why it has to be onto? So we have a G2 set. Yeah, the G2 set is not a coproduct of any other G2 sets. The regular G2 set is not a coproduct. And if this is not 1 to 1, then it's going to be coproduct because G2 is have more than one orbit with respect to the action. Okay, why isomorphism? The map has to be bijection on the level of isomorphism classes. So again, why it is onto. So if we have an I'm writing. if I have some isomorphism class in gamma 2, which is not coming from an isomorphism class of gamma 1, then you can put a G set which is empty everywhere, a gamma 1 2 set which is empty everywhere except to this point, and then it's pullback going to be the empty one, so it's going to be mapped to the initial object, self not initial object, so it can be reversed. Why it has to be one-to-one on the level of isomorphism classes? Yeah, because otherwise, if you have two isomorphism classes in gamma 1 that maps to the same one, so you can pick up a representation here and representation here, and G1 set here and G1 set here. And why are we doing there? No, they will not map to the same one. We can pick up the trivial one here. The trivial G representation that just maps this point to the singleton. Or the one that just maps this point to the singleton. I don't know, we're doing. Well, yeah, and the one that maps this point to the singleton or this point to the empty set, you cannot get it at the pullback of anything because these 2 points have to be mapped to the sets. So probably there's an elegant proof of this statement, but it's really easy. Like we can do it by hands, case by case. Should I repeat why I did it in? Okay, so first I want to show that phi, so probably there are much better proof. I want to show that phi is onto on the level of isomorphism class. So if we have isomorphism class in gamma which is not covered, we can take a representation gamma 2 sets that gives you the empty set for everything except of this isomorphism class, but do not give you the empty set for this class. And then when you put it back here, you get the empty gamma 1. The empty one gamma 1 set was initial object, and here we have so it means that it's functional map non-initial object to initial object. Purest category has to be initial object to initial object. Now why it is why it is one-to-one of the level on the level of isomorphism classes. Suppose you have two isomorphism classes here that maps to the same isomorphism class here. So you can construct in gamma 1 a G1 a gamma 1 set which will make this isomorphism class with a singleton, and then also morphism sort activity, and all the other isomorphism classes to 0. I claim that you cannot obtain this gamma 1 set as a pullback of any gamma 2 set. So of any gamma 2 set. Why? Because if you have F gamma 2 set here, these two objects, they are both maps to this object. When you pull back to gamma 1 set, you have these two maps, the sets. These two objects have to be mapped to the same to isomorphic sets. So the singleton is not isomorphic, not objective to value. So this proves that phi is bijection on the level of isomorphism classes. So you can just concentrate on one isomorphism class and ask what phi does. So phi is just a map between BG to B from BG1 to BG2. And now it's statement in group theory. If you have a morphism between the groups, so map between a function between BG1 and BG2 is the same like morphism between G1 and now if you have a morphism between two groups, is that induces equivalence of categories between the categories of G sets, then these morphisms have to be isomorphic. And again, you just prove it have to be one-to-one, it has to be onto, so it's isomorphic. I'm sure that there are better proofs, but this is and now the idea is that instead of proving directly the Van-Kampen theorem, I will prove that the category of representations of pi 1 of x sets is the same as a category of representation of the push out of this diagram. Then we have a factor, what direction for the push out. 1. I I1. So why do we have this functor? Because we do have a diagram. This is a commutative diagram. It's maybe not a push-out diagram, but it's a commutative diagram. So from the universal property of push-out, this you have to have a functor x. It doesn't have to be equivalent, but you have a functor. Now I want to prove that this is equivalence of the thing. So by this theorem, it's enough to show that on the level when you take the pullback with a projective functor, it's probably was some name f. So it's enough to show. Now I do proof of run update. So it's enough to show. F star is yes. How do we show it? So what is F star? F star is the functor for covering of x to this groupoid sets. So what are functors between push out and another category? So when we define push out, we basically define it in the following way. We said that functors for colimit in general, functors from colimit is a limit of functors from each of the individual categories. So we just do for each of these guys functors to sets, and then replace the colimit with the limit. So we replace it with 5 above. So pi, so cover of x, or 5, sorry. Cover x1, cover. So this functor gives us some functor like this, and we will need to show that this functor is equivalent. So I will tell you what is this functor. Basically, the only reason it can be. Start with the covering of x. How you can get from it covering of x1, covering of x2, together with identification of the restrictions of these coverings to y. Do you know how to do it? Forgetting about this functor. What is the only thing we can do? Only reasonable. You have a covering of x, you can restrict it to x1. Yeah, let's take the point. You can restrict it to x2. And of course, when you restrict both of them to y, you get the same covering. So,
Equivalence of continuous is just distribution.
yes, but just one. So, of course, I need to say why this is exactly f star. I will not say it, but this is the only reason we're seeing this game. So now I need to show that this is equivalence of particular. So what does it mean? Any covering that to give a covering of x is the same as give a covering of x1, covering of x2, together with identification of the restriction to y. But this is very easy. Yeah, take covering. Okay, let's talk about the case when everything is open. Otherwise, I think so we need to say something. So you need something. So you take covering of x, covering of y, of x1, of x2. You restrict both of them to y, you have an identification there, so you can just take the what is the covering in the topological space. C1 over x1, C2 over x2. So you can take the push out of the topological spaces C1 and C2 over D over. So, you don't really need D, is just a restriction to y from first to the second. The second. The identity. Anyhow, you just take this union and quotient by the equivalence relation. The two things are the same if they're both lie over y and one corresponds to the other to respect to the identification that you have. So the fact that this is equivalence contiguous is kind of more or less tautology. I mean, you can call it a Schiff condition, but Schiff condition on it's not really a Schiff, it's like Schiff of categories. So for any topological space gives you the category of coverings of this set.
Object-wise, relative.
No, but the Schiff condition, what does Schiff condition say? The Schiff condition of what? These are two categories. I want to show the two categories are the same. And indeed, you can consider the following corresponding that for any open set in a topological space give you the category of coupling. And this is a Schiff.
Is the statement that this culture is essentially subject.
No, it gives you that it's an equivalence of categories, but just you need to be careful. Schiff of what? What Schiff? The covering itself, you don't care about each covering itself. The fact that each covering gives you a Schiff is not relevant here. The correspondence that for each open set gives you a category of covering is a Schiff, but we didn't discuss it yet, so maybe. Okay, so this is kind of an abstract categorical proof of the Van theorem, which on the topological level uses the fact that there is an equivalence of categories between coverings and pi1 sets. And then all the other difficulties are mapped into this algebra. So almost no topology involved after this point. So we need to have this lemma that says that gamma that if a functor of groupoids induce isomorphism on the level of gamma sets, then it's equivalence of the level of gamma set, then it was equivalence. And then we just need to compute the dual of this functor, dual in the sense of unit dual. So it's not a joint functor, it's a joint functor which is defined on the level of pi1 sets and this seed sets. We compute it and we see it's functor of the category of coverings and the fact that this equivalence is very close. Once you compute that f star is really what you think it is, then the fact that this equivalence. Okay. I don't have too much prepared more, but there are some things that I need to say about the previous lecture, so let's make it smooth break and we can both discuss this and some tasks looking forward to say and next diagram starts more advanced stuff like probably doing other people. You want to hear about something else then how to אתם יודעים כמה הרצאות נשארו לנו?
בקריסמס אין הקצת. חוץ מזה, אני יכולה להגיד לך עוד 10 נסים.
אני יש לנו שתי הרצאות. אני לא חושב שיש יכולת לכולם.
לא הכנתי, בשנים שעברות בדרך כלל לא הגעתי כנראה. בפעם שעברה הייתה מלחמה, אז כל סמסטר קוצר, אז זה בערך איפה שעצרתי, ולפני זה אני לא זוכר. לפני זה יעשה איזה שעתיים בשבוע.
יש לי שאלה קצת מצחיקה, אני לא יכול לפגל על זה, אבל אני כאילו, לי אין רקע במתמטיקה, כאילו על הקורס הזה, אז כאילו לי אין מושג בטופולוגיה. אז מה, כאילו ניסיתי לעקוב, להקים כאילו ספציפית.
אבל מה לפי-1 אתה יודע?
לא.
למה?
כאילו, אבל...
תגיד שלא, לגיטימי לא יודעת.
לא, אבל אני לא יודע שוב כמעט...
אז בוא נספר את זה עכשיו בנקודת מבט הפוכה, של גופוליטיקה. יש מה מרחב טופולוגי אתה יודע, כן?
לא, זה כאילו זה לא עוצר אותך.
מה מרחב מטר אתה יודע?
גם כאילו זה לא דברים כאילו בערך ממש אבל לא.
מרחב מטר זה דבר הכי פשוט.
כן, כן.
קבוצה היא משחק מרחק שאתה אומר שלו. חד ולמדת, כן? פונקציה רציפה מהר ליער. אז אם נסתכל על ההגדרה של פונקציה רציפה מהר ליער, אתה בגדול רואה שמשתמשת במושג מרחק. שיכול אפסילון קיים דלתא כך שהאפסילון סביבה ובא בתור דלתא. אם אתה יכול להגיד את המילים אפסילון סביבה, אתה יכול להגיד מה זה פונקציה רציפה. וזה אני צריך לשאול לפני חודשיים. כבר דיברנו על הדברים האלה כדוגמה.
לא,
זה רק דוגמה אחת, זה לא נורא.
אני לא עומד לעצור אותך כל פעם שאתה מסביר.
לא, אתה יכול לקרוא אחרי הפיור. אין שעות קבלה, אבל אפשר לקרוא את מי שאלה.
כן.
יש לך מושג של העתקה רציפה בשתי מרחבים מטר. אם אתה רוצה... יש המון דוגמאות מרחבים מטרים, אבל אני מנסה הרבה מאוד דוגמאות של תתי קבוצות של הרב. כל תתי קבוצה של הרב נותנת מרחב מטרי, ואז יש מושג של העתקה רציפה בין תתי קבוצות של הרב. זה כבר המון דוגמאות, כן? כל דבר אתה יכול לצייר, לדמיין בתת ממד, או לדמיין בדמיון יותר גבוהים. למשל, יש לך מעגלים, ספרות, אלמנטיות, טורוסים, פה כל הכיף. עכשיו, יש עוד דוגמאות שהן פחות טובים, כמו למשל, גם מרחב מטרי, גם מרחב טופולוגי. אז במקום לדבר על הקטגוריה של מרחבים מטריים, בואו נדבר על הקטגוריה של מרחבים מטריים ובילים. במקום לדבר על הקטגוריה של מרחבים טופולוגיים, נדבר על הקטגוריה של מרחבים טופולוגיים וטרייסבילים, והיא שקולה לקטגוריה של מרחבים מטריים, שהעתקות הן העתקות רציפות. זה אומר שזה בעצם די מתעלם מהמטריקה, וזה זוכר רק משהו מאוד חלש של המטריקה, מה זה רציפות. בשביל להגדיר מה זה רציף, אתה בעצם אפילו לא צריך לדעת מה זה כדור, אלא רק צריך לדעת מה זה סביבה של נקודה, או באופן כללי מה זה קבוצה פתוחה. המושג של טופולוגיה זה מושג אבסטרקטי שאומר מרחב שבו הגדרת מה זה קבוצה פתוחה. זה צריך לקיים כל מיני אקסיומות. אבל אתה יכול לשכוח מזה, 99% מהמרחבים הטופולוגיים שתתקל בהם יהיו פשוט מרחבים מטריים, או ספציפית תתי קבוצות של RN, מספר טופולוגיות קטגוריה מאוד ישירה, אבל אני לא מסתכל על איזומטריות ביניהם, לא מסתכל על העתקות ששומרות מטרו, זה יגיע לדבר על מטרו. אלה העתקות ששומרות, אלה העתקות רציפות. וזאת הקטגוריה של לא כל המרחבים טופולוגיים, אבל כל המרחבים טופולוגיים שקרה בגבול. אפילו לא צריך לדעת מה זה מרחב מטרי, פשוט צריך להבין מה זה העתקה רציפה בין שתי קבוצות של הרב. יודע, פשוט עובר על ההגדרה של אינטראקציה. אז מה זה הגרופואיד הפונדמנטלי? אז כל מה זה מסילה במרחב טופולוגי או כזה מרחב. אז מסילה זה העתקה רציפה מהקטע הסגור למרחב. גם הגיוני לפעול מסילה ברור. כל נקודה בקטע הסגור יש איזושהי נקודה במרחב, אני יכול לצייר את זה. במסילה יש נקודת התחלה שלה ונקודת סיום. מה זה הומוטופי במסילות, אתה יודע? אז תחשוב שיש לך סרט וידאו שמתחיל במסילה אחת ונגמר במסילה אחת. אז זה אומר ששתי מסילות הן הומוטופיות והסרט וידאו, סרט וידאו זה לא בדיוק מושג מתמטי, אז דרך להגדיר את זה, זה העתקה מהריבוע למרחב שלך X. עכשיו, אני רוצה הומוטופיה ששומרת על נקודות הקצה, יש סוגים שונים של הומוטופיה, אז עכשיו אנחנו רואים הומוטופיה ששומרות על נקודת קצה, אז אני רוצה שהנקודה הזאת תמיד תועתק לאותה נקודת התחלה, לא תמיד לאותה נקודת סיום, זאת אומרת כל הקטע הזה בריבוע, כל הקטע הזה בריבוע, ויותחו לאותה נקודת התחלה ואותה נקודת סיום. פה יהיה לך את המסילה הראשונה ופה את המסילה השנייה.
איך הגענו לריבוע?
אז מה זה סרט? סרט זה לכל רגע זמן, נניח סרט לוקח דקה אחת, אז לכל רגע זמן או שנייה אחת, לכל רגע זמן בין 0 ל-1, אתה רוצה סטילס מהסרט, כן? שזאת בפני עצמה תהיה מסילה. זאת אומרת, לכל מספר ב-0 ל-1 אתה רוצה מסילה. אבל סך הכל, מה זה מסילה? מסילה זה גם העתקה מקטע 0-1 לירידה. זה המרחב, אז אתה רוצה לכל זוג של מספרים בין 0 ל-1, נקודה. העתקה מהריבוע למרחב. הריבוע הרי בנוי מהרבה סלייס, כן? וכל סלייס נותן לך מסילה.
זה יותר השאלה שלי, לאורך קורס, כאילו, אתה נותן הרבה מאוד דוגמאות וכל מיני דברים שאני יודע מבין זה בתוך אני מנסה להבין קצת מההרצאה הזאת, מה התגובות יותר בגלל הכללי.
ההרצאה הזאת הייתה כולה על דוגמאות, כן? הייתה על שתי דוגמאות, על אחת בתורת ההצגות, על תורת מקים, והשנייה בטופולוגיה גלם, כן? אז כדאי להבין את הקורס, לא חייבים לדעת את כל החומר רקע, אבל כדאי לדעת איזשהו אחוז מספיק גדול כדי להבין תורת דוגמאות.
כן, אני הלכתי על זה גם הפוך, אני מנסה לזקק את
לא, אבל אני חושב שכן כדאי להקיף את הקורס, אני מתאים לך במידה. עכשיו, כאילו, ברור שלהשלים 3 לימודים של תואר ראשון במהלך קורס אחד זה לא מאוד פרקטי, אבל לא באמת צריך, כן? אתה יכול להבין את הדוגמאות גם בלי לדעת. באתם מזה עכשיו?
כן. כי במקור יש הרבה שימושים לזה
כן. כן, אבל למרות שאני לא יודע מה הם, אבל אני רואה.
אני לא יודע אם באמת תכננת, אבל דווקא מונדים דווקא זה משהו שאמור להתקדם.
אני לא יודע אם דווקא החלטתי לוותר הפעם, אבל אני יכול לנסות. אני פשוט לא כל כך זוכר על זה כלום.
טוב שהזמן.
כן, שאני לא זוכר על זה כלום, אז אני צריך ללמד. אני לא פעם למדתי מה שצריך, אבל פעם אחת עשיתי את זה בשביל איזשהו קורס. מישהו הקורס הזה, כן. מה אני רוצה לציון? טוב? יש לנו עוד 5 דקות, כן?
That's it. Yeah. Yeah. Episode station. I'll send you.
להמשיך להגיד על אחד? אז מה זה הומוטופיה בין שני מסלולים לחזור על זה או שזה היה בהם?
כאילו אם יש לך מקטע סגור, כאילו זה לא יכול שוב פעם קטעים
הרבה הרשאות מקטע סגור לסטיקס הפסיכולוגי שלך
אדם צריך הרבה העתקות.
זה הומוטופיה, מתחילה מהעתקה אחת ונגמרת בהעתקה שנייה ובכל רגע זמן T באמצע בין 0 ל-1 יש לך העתקה מקטע סגור ל-X. זה סרט אנימציה, כן, שמתחילה במקום אחד וגומרת בהפרמה חשמלית. בואו ניתן לנו איזושהי דוגמה, יש לי שתי נקודות במישור ויש לי את העקום הזה שמתחבר ביניהם ויש לי את העקום הזה שמתחבר ביניהם. אז הם הומוטופיים, כי אני יכול להתחיל מהעקום הזה ואתה יכול לדמיין לעצמך המון 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 עקומים באמצע. זה בכל אנימציה, כן, זה עכשיו בכלל רצף שלנו, כן? שבסוף מגיעים לשני. אבל לדוגמה, אם יש לי, הוצאתי איזשהו עיגול או אפילו נקודה, ויש לי את העקום הזה, אז הוא כבר לא הומוטופי לעקום הזה. אתה לא יכול לעשות וידאו שמתחיל מהעקום הזה, אסור לך לעבור דרך העקום הזה, הוא לא חלק מהקבוצה, אז אתה לא יכול לעשות וידאו שמתחיל מהעקום הזה ונגמר בעקום הזה. הוא יפריע לך באמצע, כן? זה חפר. לא חפר. אפילו מגומי, זה הרעיון בטופולוגיה זה שהכל כזה מאוד מאוד גמיש. כל דבר רציף מותר. אסור לקרוא, אסור להדמיד. כל השאר נסתר. רציף זה בעצם אומר שאסור לקרוא. ואם אתה רוצה משהו שהוא שקילות, שהוא מופיע, אז כאלה שני כבדים, אז אסור גם להדביק. להדביק זה אומר שלכיוון השני, הדקת התקרה. אבל פה בעצם אנחנו צריכים להדקות רציפות, מותר לו להדביק, מותר לדברים לחתוך את עצמם אפילו. אבל אסור לנו לחצות את העיגול בלי, כי אנחנו לא יכולים לחצות את העיגול בלי לקרוא. טוב, אולי עכשיו נעשה הפסקה ולשאר שבת אחרי הפסקה. Okay. So we can continue. So, yes, so I wanted to talk about two things that I somehow forget in the process. One is the bottom group, which I want to talk about this million category. Another is the other notion of shift that we say we will call Gothenburg shift. So, yeah, which I wanted to discuss when we discuss equivalence. So what is the Gothenburg group? So you remember in the billion categories, we have the notion of kernel and co-kernel, and this gives us an important notion of exact sequence. Yeah, so our work serves the notion of image and co-image, whatever, and they're the same. So exact sequence in general, A, B, this can be a piece of a longer sequence, so we say that this very short exact sequence is exact if the image of the first morphism is equal to the kernel of the second. And there's more general notion of a complex where when you first apply the first morphism and then the second you get 0, each time you have 2 consecutive morphisms, which means that the image is included in the kernel and included what has been included, so they are both sub-object of D. something that we also didn't discuss. What are sub-objects of a given object? So if we have a category C and we have an object X, so subs X is part of the over category. It's also monomorphisms from Y to X. And this is a category, but an exercise, I hope it is correct, but certainly it's correct for a Boolean category exercise. So the sub of X is the more accurate, it's equivalent to a positive. So, but it's not equal to a positive because you have many automorphisms of X, so there are many different. X itself is sub-object of X in many different ways, but all these ways are isomorphic. So if this would be the only object, then we get just two. The category which is equivalent to the trivial category, one isomorphism plus no.
So could you say once again what is sum?
Sum of X is a subcategory in the over category of X, which requires that the morphisms are monomorphic. So pair of objects and monomorphism to X. This is a full subcategory of the over category, and it is equivalent to a positive. And in cases that you know, like sets, vector spaces, whatever, it's exactly the category of the poset of sub-objects. Exactly, I mean it's equivalent to the poset of sub-object. Because if you take a set, then this will give you the collection not of all subsets, but of all pairs, set and embedding into your set. There are much more such pairs than just subsets, but not interesting anymore. Okay, we can have many different sets with many different embedding the same set. But if the image is going to be the same, then they're all going to be the same, they're all going to be isomorphic in a unique way. So you don't really add new information, so this category is equivalent to the category of or to the poset of subsets. Yeah, so the image and the kernel are both sub-objects in B, and to say that one is included in the other means just you have a morphism from one to the other. It's equivalent to say that the composition is going to be zero. But if they're equal, so in this case we say that it's a complex, and if they're equal, we say it is a that's this exact sequence. Now usually when we discuss exact sequences and complexes, we discuss infinite sequences. In that case, we mean that they are exactly equal. And okay, so what are maybe the shortest possible? So what we do only infinite sequences, but what does it mean that we do something short, or we want to consider something finite? So we just pad it with zeros. So if we have anything finite, we can add zeros, and then we can consider them infinite. So length 0 exact sequences is going to be just complete 0, but then padded with zeros, and we just get a sequence of zeros. It has no information. So what can you say about sequence like this? What does it mean that such sequence is exact? So
Logically.
do you mean topologically?
Tautologically.
No, it's not always exact. You said the correct answer. A has to be isomorphic to 0 or equal to 0. Because the image of this map has to be equal to the kernel of this map. The kernel of this map has to be everything, and the image of the map has to be 0. So if 0 and everything is the same, then the entire thing is 0. It's tautologically a complex. Yeah, such sequence is always complex, but it's not always uniform. Now we have A, B. What does it mean that such sequence is exact?
The average is 0.
The what is 0?
The average.
That's-
It's isomorphic to B.
Exactly. This map is isomorphic because its kernel is going to be 0 and its co-kernel is going to be 0. Because the image has to be equal to this kernel. So
Only for the identity.
What?
Only for evident.
Yeah, now we're talking about the notion of a exact sequence is kind of usually this in the context of Boolean. You can play with it, but it's not what usually. Okay, so until now we didn't get anything interesting. So the shortest interesting thing that we can get is called short exact sequence, like A, B, C, padded with 0. So when somebody says short exact sequence, it means this. Yeah, it's not the shortest possible exact sequence, and yeah, it's maybe even shorter, but then it's not padded with 0, so we don't like it. No, we sometimes we consider it actually. And so this is short exact sequence. So what does it mean that we have short exact sequence? How we can see it? What does it mean about this map and about this map?
From each of these all X.
Monomorphism, it has to be embedding monomorphism because the kernel is low. And this map, epimorphism because the co-kernel is the image mentality. So we can think about the object B as a central layer here, and it has a sub-object A because monomorphism is a sub-object, and we have a quotient object because epimorphism is always a quotient object. If we short quotient object, same. So basically, we have B, we have a sub-object, and when we quotient by the sub-object, we get what has been to quotient by a sub-object is just taking the co-kernel. So I didn't say anything new. And so we have B, C. So phi is monomorphism, C is epimorphism, the co-kernel of phi is C, and the kernel of C. And so in this case, we say also that B is an extension of A and C. And the most basic extension is the direct sum. The direct sum of the object is extension because we have embedding basis and projection basis. And do you know? Can you give me an example of an extension which is not direct sum? Which is not like a mode direct sum. What? Jordan blocks. This is a good example, but okay, but then we have to explain with you. In what category you are working?
Consider category of modules of the polynomial ring, one variable. We have two nice modules with clear election of x. So consider C of x modules. Well, let A and C be just a trivial module. So A.
What do you mean trivial model?
A is a module to C is a module to C. Just
Well, the C and what is the action of C of x on C?
X acts by 0.
Yes. And what's going to be B? Oh, we said Jordan block. So it's going to be two-dimensional space. But the action of x will be given by this matrix. And now we see that you have invariant one-dimensional space in which the action is 0. So you actually have a map from A to this two-dimensional space. And you have a quotient by this one-dimensional space, which is going to be another one-dimensional space on which also the action is 0. So this matrix is not 0 at all, but for the quotient, it's going to act like 0 because its image is equal to its scale.
Also say Z goes to Z goes to Z.
Okay. So I want to finish this example. Of course, it's not the simplest example, but this is important example. You put here C, you put here C, and you put here this two-dimensional space C2, but with non-trivial action polynomials, and then you see that it's not the direct sum because the direct sum is actually going to. But now you have a simpler example, which is maybe the simplest example you can think of. So in what category you're working? I'm building books. Z goes to Z. How does it go to Z?
And
Huh? and the quotient going to be z over 2. So this is a short direct sequence, and in any way this direct sum is not z. And another example, which is for some perspective even simpler, because this is the category of abelian group, which is nice and complicated because it's big, because there are infinite guys in there. So let's talk about category of finite abelian. And in finite category, the category of finite abelian groups, basically the same example, or the simplest example that you can think of extension which is not direct sum.
Well, it's C4 by C5.
So this is a cyclic group of 2 elements, cyclic group of 4 elements. The Sitter and the Klein group and the cyclic group of 4 elements are different groups, are not homomorphic. Here you have element of order 4 redundant. So there are lots of extensions which are not direct sum. Now one has to be careful. What do we mean when we say that extension is a direct sum? So naive way to define it is that just this object in the middle is isomorphic to a direct sum. And in all the examples that we saw here, there were not direct sum given in this sense. But of course, this is not the reasonable way to define it. So if you want to say that the extension is a direct sum, so another direct sum, you don't just want to find another of the heap. So we have these two extensions. So another you have another exact sequence, this exact sequence, and to say that they both give you direct sum, it means that you have an isomorphism such that these two triangles are comes to diagonal. This diagonal. And of course, in all the examples that you said, there are no direct sum, and maybe an exercise with star to find an example where, like, abstractly the extension will be isomorphic to direct sum, but it will not be direct sum. A bit more complicated, but of course I don't. So extension does not have to be direct sum, but it's somehow similar to direct sum. So the behavior of the object in the middle can be somehow understood in terms of the behavior of the two other objects. And the idea of Gaussian group is that we start with a abelian category, and then we forget. First of all, we forget most of the categorical structure. Basically, want to think only about eigenvalue classes, but we do want to remember the structure of direct sum, etc. And also, we want to forget the difference between direct sum and other extensions. And then we see what we get. So this is called K of category C, and how they are defined. So again, we ignore problem of set theory, but you can always replace C with small category and then that's problems. Oh, not always single. If C is generated by a small category. So you take the free abelian group generated by object of C. Modulo, now I want to put relations, and what will be the relations? Basically, the relation will be that each time you see extension, you can replace it, even not with direct sum, but just with the abstract sum here. So each time we have A, B, C, we say that B is equivalent to, let's call it like this, A plus. This is even not the direct sum, but just the abstract sum here takes a full. And this is the definition of Gaussian group. So let's do some examples. What is a Gaussian group? Or maybe before I want to say example of sometimes you cannot have non-trivial extension. For example, in vector spaces, if you believe in the axiom of choice at least, there are no non-trivial extensions. Any extension, maybe not in a canonical way, but any extension is isomorphic to some extension, other extension. So this diagram going to be not canonical isomorphism, but is isomorphism of extensions. Do you know how to prove it? You have a vector space, a subspace, and the quotient space. How you make it isomorphic to a direct sum?
Well, you can choose a basis in a subspace and then complete it to a basis of the dimension.
Exactly. So we have V, we have W. So one way to do it, you can choose the basis for W and complete the basis to the entire basis of V. It's one of the first terms you are studying in algebra. Then you take this complete the basis vectors that you add, and you take the spread and you call it L. And this gives you isomorphism like this, V plus L isomorphic to V. And moreover, L will be isomorphic to W. So this gives you isomorphism between your original sequence and the decomposition. And this is
Sorry, what did you define here?
so here I define the Gaussian group. So the Gaussian group is not the KFC. It is defined this way. It is a free abelian group generated by the object and quotiented by this equivalence relation. Maybe you also need to add to the relations that 0 is 0 means empty.
What is it? That B is a wait. A
What
plus
is this
C
part?
first of all?
A plus y.
Yes.
So this is element in the free. So this is a free abelian group. I need a way to denote the elements there. So each object A gives you an element which I will call quotation.
If we have an exact sequence like that, then we have.
Then I declare that V is equivalent to the formal sum of A and C. Formally
Yeah.
exists. In particular, it says it's equivalent to the direct sum, but it's even stronger. And not just identified with that. Okay, so what is a Gaussian group of vector spaces? Of fine dimensional.
0 could be the case.
Of fine dimensional. What is a group of fine dimensional? You already asked the next question. Probably not. So it looks huge in the first one. You take all the fine dimensional vector spaces, you generate huge free abelian group. But then you have very powerful equivalence relation. You don't really need to talk about extensions because
But
I'm more.
also need to notice that if you have isomorphic objects in C, they give you the same object in your Gaussian group.
Yes, so we say it does follow from here, yes?
Yes, it's false, but we don't notice.
You have x, x, y, 0. This is an exact sequence. If they are isomorphic. And y is equivalent to x and 0. So this is why I think when we need, maybe we don't need this, I'm not sure. We probably don't need this because we also have x 0. So 0 plus x is the same like x, so we print.
Is it just that?
What?
Then
Yes, exactly. So the Gaussian group of the category of fine dimensional vector spaces is that equal to 0. So of course, why? So yeah, we have plenty of vector spaces, fine dimensional, but okay, one of them will be the vector space K, it's the figure.
just generates.
And it generates everything with direct sums, certainly with extensions. So now we have another vector space, the two-dimensional vector space, an extension of two one-dimensional vector space. So using this relation, you have to go to twice the
What about the negative?
it's free abelian group. So we allow to take minus. It's integer combinations of vector spaces. So we allow to take -5 times k. So this gives us a map from Z to here. So it's very easy to show that this map is onto. You have any vector space can be obtained as image of isomorphic there are some sort of indicate. I don't really know how to show. Okay, it's also easy, but okay, I don't know it for for the moment how to show it is one-to-one, but no, it is easy of course to show it one-to-one because you have the notion of dimension. And just you have this map, it is onto, and you have this map, which is the dimension map. So what does mean dimension? If you have a fine combination of vector spaces, you take the dimension of all these vector spaces, multiply by the coefficients, and sum it up. So this is more from the form that was in the group, because if you have short exact sequences, further dimension, and then you know that the composition TAC and TAC is identity, and you know that this is onto, so it's enough. Shows it. So it proves that this map is one-to-one and one. Okay, but then there was a funny second question. If you go with all vector spaces, and you say the answer, but what is the quantity group? It just becomes zero. Kind of sad, but this is life. So do you want to explain why?
Consider a vector space of all vector spaces. You can consider just infinite direct sum of copies of B.
Your vector space is E or V?
B. So I'm not going to consider any exact sequence. I just want to say that consider a class in Grothendieck group of infinite direct sum of copies of B. Then it's definitely isomorphic to V plus the same space, the same direct sum. So that means that class of B plus class of this infinite sum is equal to class of this infinite sum. That means that class of B is just zero.
So let's write in exact sequence, so we didn't want to. So I take V plus mapping it to the first column. So this is one map. Now here you have projection to all these coordinates. So this is a short exact sequence. Now this and this gives the same element in the quantity group. This has to give a difference. So needed to go. So very sad, but this was it. Now what happened with a quantity group of say finely generated opinion?
Direct sum of infinite copies of Z.
So we want it to be like some of infinite copies of Z because we have Z and we have powers, but also we have Z and cycle group C2, we have C3, and each of them kind of hopefully gives you a new element in the quantity group, and together you get many copies of Z. But again, it doesn't work for similar reasons. Most of them dies. So what is C2 in the quantity group, cycle group of two elements? It has to be zero because you have an onto map like this, and you have a kernel like this.
So it's telling.
So yeah, then again, so the only invariant that we left is the rank. And finally generated Boolean group has the rank, how many copies of Z are inside there. And this is and then it's to get. Okay, but what do we do if we want to get something more interesting? So what category we should discuss? Like finally generated Boolean groups, but slightly different. Finite Boolean groups. We will not actually, okay? But we will get all that. So any finite Boolean group is not a direct sum of prime cyclic groups, but it is an extension of prime cyclic groups. So the Gaussian and in a unique way. So the Gaussian group going to be just it's a free group generated by the prime sequence. And the Gaussian group of general groups is not well defined because we didn't talk about because it's not a million. So, okay, before we talk about C of X, what is the Gottlieb group of three of C of X models? Finely generated C of X models. So non-finely generated are probably going to get 0. So yeah, just the same argument always work. We have a key in that example, we don't get anything good. So a finely generated C of X models. What's going to be the Gottlieb group? For the same reason, you again get Z, because you have a free C of X model, and then you have a model, you can, any model M, and you can map on it the free C of X model with some power, and the kernel going to be also free. Submodels of these models are all free because C of X is PID. Okay. So this is called the resolution, a free resolution, and in this case you always have very short free resolution. So any model going to be difference the Gottlieb group of these two guys. So we only care about the number n, which can go so negative. But if you want finite dimensional C of X model, so finite dimensional means finite dimensional over C. Then you get a free abelian group generated by all points in the complex plane. Because any point in the complex plane give you a C of X model, a one-dimensional C of X model on which you act with a scalar given by this component. The X one-dimensional C of X model, you just need to specify how X acts, so it's just n. So these are the So and this is very common. So in many categories, if all any object is finite extension of simple object, so simple object is an object which is not extension of anything else, non-trivial. So you have no sub-objects except of 0 itself, like prime numbers. So if any object is finite extension of simple objects, like the Jordan-Holder situation, then the Gottlieb group is just a free abelian group generated by this. And sometimes it happens and sometimes not, because if you allow infinite things, then your infinite thing can swallow the finite things and make them simple. If you allow all infinite things in your category, like if you have infinite direct sum, then you just keep that. So the second topic I want to discuss is the notion of shifts. So we've already discussed the notion of shifts according to Leré. I didn't say what are shifts of with values in other categories. So usually you can define, depending on the other category, but usually you can define it as like shifts with value in C object in the category of shifts. But if we concentrate in the case of abelian groups, which is maybe the most important example of shifts, except maybe of sets, the shifts of abelian groups are like Leré shifts of abelian groups, so like map from X tilde to X, such as locally so isomorphism, like open embedding, and we also have a structure, one abelian group on each of the fibers, and the structure of course has to be continuous. So just abelian group object in this. So now let's discuss the Gottlieb definition, which is kind of from the beginning built to define shifts with value in C, but we can do it also in sets. So we start with sets, but okay. So first of all, what is square shift on X? So if you have a topological space X, you remember we have this category top of X. This category of objects are open sets in X and it's a possible. So you remember what are per shift on a category? Just functors, contravariant functors to sets. So this will be my definition for a shift. So for each open set, we need to give some set for now. which we will call the sections of the sheaf over this. Okay, but this is just a per sheaf. In order it to be called a sheaf, we need more information. So we need to be able to glue sections. So the way we think about the sections is like here, but for each open set in X, we have the base change here, and then we have the notion of sections, just set over continuous maps like this, and which are sections. So that when we do this and then go downstairs, you get one-sided units. So a choice of element here, or element in the fiber for each point. So sections are some kind of functions with changing values. So for each point we have different values, different possible values, because the fiber is different, but we think about it as some kind of functions. And the idea is, what the shift condition says to you, says that if you have two open sets, or many open sets, let's start with two, and you have section here and section here, which agree on the intersection, then we should be able to construct in a unique way section on the entire thing. So, and what is a shift and condition? So shift F, a shift on F is a shift. Okay. Such that for any U union UI. So each time we have an open cover, the following is an equalizer. We have the following equalizer diagram. So what's the diagram? We have f of u. So you remember that sheaf is contravariant factors from the concept of open sets, so we have f of u. So it maps to each of the f of ui because it's contravariant factors, ui are inside u, so we map to that direction, so we also have to map to the problem. I here we have two maps. Square f of ui intersection. So ui intersect with uj is subset both of ui and of uj. Here, like we run an ordered pair, so I equals j. So we can choose that these guys are all like embedded into ui, or we can choose that these guys are all embedded into uj. So we give you two maps from here to here. So you get here two maps, and you want this thing to be equalizer diagram. So it means that this is an equalizer of these two maps. Now this is shifts of sets, so it just means that we know what is equalizer. We don't need to use the theoretical notion of equalizer. So it means that so it means two things. First of all, any element here is uniquely determined by its restrictions to UI. Restrictions, I call it restrictions, but just the application of our function. Each UI, if we're embedding from UI to U, we can we have this notion of restriction. So we have the fact that F is a shift functor, so give us map of restriction map here. So if we know all the restriction map, we know that. So this means that the map from here to here is one. So also the map to the equalizer of one. And the second thing is that what is the image? So the image is of course not everything, not every choice of section on each of UI comes from section on U. But if they agree on the intersections, which exactly means that these two maps are the same, so means that you're agreeing the equalizer, then it has to come from U. So this is one way to phrase it, but now that since it's a course in category theory, we can phrase it even better. We can say that the map from f of u with a limit of the diagram f of u J, UI. Okay. So we have this diagram, but I and J are running. So big diagram for any I. Then for any I, we have an object here, and for any pair I and J, we have an object here, and then we have for each time that I is inside the pair IJ, it might be the first or the second. We have a map like this. Maybe I should write it. Yeah, but the range of all UI and J, so we have a big diagram, we take limit, so I want this map to be something. Definition. In the press shift such that for any so this was definition 1, and this is equivalently the nature map from here to here is so this is an algorithmic extension of a sheaf, and we just now defined it for any for sheaf of sets, but now you can just replace the word set with any category C. Sheaf of objects in C is a press sheaf of objects in C, so we just quantify factor to C, such that you have transformation. And I'm not sure if I check it, so under what condition press sheaf C is the same. Yeah, there should have to be some condition because we have to forget to factor from C to sets. So what's the condition for forget to factor? Yeah, probably just the factor should commute with equalizers or commute with limits. That problem. Okay, so sometimes the shift condition is divided into two pieces. The first part, and this is 1-to-1 first shift condition, and the second part that the image of this map is exactly the equalizer is the second shift condition. And press shift that satisfy only the first shift condition is sometimes called decent press shift. I think this is called. What?
You say once again.
Louder.
Would you say once again?
First condition, second condition.
Yeah.
So
What's the term?
shift condition sometimes are decent press shift. I think that press shift that satisfy sometimes called separated press shift. Yeah, that's a many names. But yeah, usually it's not. We will discuss at some point we will need this. Yeah, it's a theory, but. Okay. So now a nice theorem. Where two now think what makes shifts and Lara shifts. So a nice theorem is there equivalent. Theorem. Lara shifts on X is equivalent to Gaussian. And of course, we don't only interested in the general knowledge that just the things are equivalent, we also want to have an explicit equivalence. And there is very nice explicit equivalence to this direction, and not that nice, but also okay equivalence to this direction. So let's define this equivalence. It's very easy. Assume we have another sheaf, we want to construct bottom sheaf, and this is how to do it. So the bottom sheaf corresponding to a Lara sheaf I from middle to.
So could you once again, this is a theorem for any
topological space. I guess really any topological space, but you can assume that it's reasonable. But I don't think you need to assume it's reasonable. Okay. Not out of whatever. So what is the definition? How to define starting with the Lara sheaf? How to define a block? Okay, sir.
next section.
So we need to take section. So I want to define the bottom sheaf. on some space U. I define it as a collection of all functions of U. Tilde, which are sections. What do it mean? That first perform F, then perform phi is equal to F. Identity, its image is U and not X, but so okay, so why in the shift? It's kind of tautological, yes, for any. If you have a section and you know its values on each open set, then of course you know its values for any point. So you know, and if you have a section which is defined on each open set and agree on its intersection, then now you can define it for any point. You need to just choose one open set that includes your point, and then you use it for each. And if you choose the wrongly or choose different open set, then you get the same answer, so it's okay. And so this direction is easy. What about the other? Okay, this is probably hard to guess on the spot. So the other direction, it's kind of really complicated construction. You can starting with any shift, construct any cosmic shift, construct LR shift. Let's do it. Then we'll do very quickly. So for this, we need to define the stop. So for any ignition, that go to the shift X. So we can define the stop of F at the point X. How we define it is equal to limit over all open sets that includes X. And so why is that? What do we mean by limit? So this collection is a poset, so it's a category, so we have a shape of the diagram. And this F is quantavariate functor, so we have maps when U becomes smaller and smaller. And then we take limit over all this diagram. This is kind of a huge object, and then we define X tilde to be as a set that is joint union of F's. So over each point, we just place this. But now I have to define topology. And how do I define topology? It's kind of hard because I don't know how to glue this thing together, but I do know what I want. At the end, I want that all the sections of F, so all the elements F of U, will actually give us continuous sections of this thing. So how do I do it? So I just take the, I don't remember, strongest or weakest topology such that all these maps are continuous. So let's define, I will just define open sets. So let me define O U F. So if F is element here and U is an open set, then define O U F to be the following collection. X U and the class of F in the stock. This F is a section of U, F is element U. So it will give you this limit, which will move on the class of F. So and we take this set. This is subset in X. So we declare this set to be open, and then we take the topology generated. And this ensures that all the sections F going to be continuous sections. For image of an open set, I have going to. So okay, we constructed it. So at least this ball array. So we constructed. Also probably this was invented by array instead of algorithmic, because invented this category and probably did discuss sections of shifts, and then algorithmic realized that you just need to know what are the sections and you can forget about the geometric objects that represent the shift and then define this general notion of a sheaf and show the equivalence. So you can start with this. And so the statement is that this equivalence of categories, maybe we'll do it next time. It's not so that hard. Usually we need to show something. We face one section is objective, exists direction, it's the easiest, and it's enough. But this is a bit weird equivalence. So why it's weird? Because here we have very lots of natural nice sheaves, for example, carbon. Yes. But here we have very so we also have sheaves that comes from covering. For example, if you start with the maybe I will tell next time. So you have sheaves that come from coverings, but you also have other sheaves that's very natural from this point of view, and here look complete disaster. So for example, for any topological space, you have the sheaf of continuous functions. What does it mean? For any open set, you just consider the vector space of continuous functions. And of course, you have restriction of continuous functions, so it's a sheaf. And if you have a continuous function on each open set, you can glue them together to get a function, so it's a sheaf. Now you can ask, what is the corresponding Larache sheaf? And the answer is a total complete disaster. Let's just imagine it for any point x. You first of all consider stocks of continuous functions. This is a reasonable option. Continuous function up to equivalence, a continuous function defined in a neighborhood of x, up to equivalence relation, the two continuous functions are considered the same if they are equal in some smaller neighborhood. A reasonable object, but very large. So there are lots of stocks of continuous functions. So basically as much as continuous functions. Now, of each point of x, you put, so this is a large thing, but you also assume that it probably has some reasonable topology, yes, continuous functions that can vary continuously, you can talk about when they have to explore it. But you completely ignore this topology, and if each point you plan this huge stock, but at a discrete set. And then for two very close points, this continuous function somehow, this stock somehow can be related. So you do have topology on the horizontal level. But each continuous function gives you some stock at each point, and this is going to be continuous family. So this is completely non-Hausdorff space, because over each point, all this million of continuous functions, it's like the fiber is discrete, so each of them is kind of isolated in the fiber, but once you move a little bit outside the fiber, nothing is discrete. So any two stocks can be connected outside the fiber. So you can't really find a neighborhood that will not intersect. Yeah, it seems. So any 2 points in the fiber are not separated like T2. They're not like separated. So this very natural bottleneck sheaf is completely disaster at Larache. And also you can do smooth functions if you're talking about manifolds, or polynomial functions if you're talking about algebraic variety. And in fact, one of the ways to define geometry is just consider a topological space with some sheaf of functions that are kind of represent your geometry. So if you want to do general topology, you will do continuous functions. If you want to do smooth manifolds, you do smooth functions. If you want to do algebraic geometry, you do polynomial functions. You can do analytic functions, and you can do even sheaves which are not really sheaf of functions, just sheaf of algebras, which you think of as functions. And then you get things like theory of schemes, etc. So these sheaves are very, very natural from the point of view of how to define geometry, and completely unnatural from this point of view. What are the natural guys from this point of view? So the first natural guy is a constant sheaf, which just means several copies of x. What is a constant Gottlieb sheaf? Any guesses? Oh, you said it is right? What?
It's gonna be the end of the lesson,
Yes.
and that's great.
Yeah. Break for one. Mine's. So what is, if here we have like many copies of x maps to x, what will be corresponding Gottlieb sheaf?
locally constant function.
Locally constant functions with values in this set of copies. So if you have 5 sets of copies, so it will be locally constant functions to a set of 5. It will not be constant functions, so it's called a constant per sheaf, but a constant sheaf, but it's not just constant functions. We could just say constant sheaf, maybe it's the sheaf that for each open set give you the same constant value, some set of 5. And but this is a per sheaf, but it's not a sheaf, because we can't glue things if 2 open sets do not intersect. Here we have one value, and here another value, and then we can glue them together to a constant function, but we can glue them to locally constant function. So locally constant sheaves are perfectly okay with both points of views. And next time we'll discuss what common represents here. But... So see you in a week. עכשיו אני בבעיה כי אני צריך לשירותים. בקרוא את זה. איך סוגרים את זה? כך.